Let's look at alkenes now and their properties. So in this section, we want to talk about the alkene nomenclature and some of the physical properties and some applications of alkenes. Let's start with nomenclature. Nomenclature rules are pretty standard the way they were before, which means that you have to name the parent hydrocarbon, which means that the longest chain, okay? So you have to count the longest chain again, but this time you need to make sure that the double bond gets the lowest number possible, okay? So even if it looks a little bit weird, okay, like in this one, then you still have to make sure that this double bond is counted as within the chain, not outside the chain, okay? And so 1, 2, 3, 4, 5, this is a pentene, and it's not going to be 1, 2, 3, 4, 5, 6, okay? So it's not a hex, all right? So not a 6-carbon chain, but a 5-carbon chain, because we don't really know how to name this, okay? And so even otherwise, the rule is you start from the double bond, okay? So that's the one thing. The next thing is then, of course, you find the substituents as usual, all right? And then you arrange everything according to the double bond, all right? So give the double bond the lowest number possible, and then everything else is going to be according to the double bond, and then, of course, alphabetically, all right? So if you have a methyl and a chlorine in the same one, in the same compound, then you give chlorine the preference, and then the methyl, and then whatever alkene you have, okay? So the nomenclature then is something like this. So for example, if you have a 6-carbon chain like this, you start the numbering from the right-hand side and not the left-hand side, because this is closer to the alkene. So 1, 2, 3, 4, 5, 6. So it's a 6-carbon chain. Now always remember that the double bond is actually between 2 carbons, 2 and 3, or whichever 2 carbons. So you have to pick the lower number, okay, for this. So the name then for this compound becomes 2-hexene, all right? The new nomenclature we'll talk about in class also a little bit. It's a little bit weird. It's hex-2-ene, okay? So you give the number just before the functional group, okay? And so it's a little bit weird, and a lot of books still do the old one, okay? In this case, in the right-hand case, you start the numbering from the left-hand side. So 1, 2, 3, 4, 5, 6, again 6 carbons. On the second one now, you have a methyl group. And so then 2-methyl-3-hexene, okay? And don't forget the dashes, okay? And then this compound, the one that was given on the top there, it's going to be 2-ethyl, 1-pentene. Okay, so you have to include the double bond in the chain. If you have 2 double bonds, then you have to obviously start from 1 somewhere. So you start closer to the substituent over here. So everything will get the lower numbers possible. And so here it would be 2-methyl and then 1,3-butadiene. The buta is for the 4 carbons. The diene tells you that you have 2 double bonds in there. Okay. So then we go on to cyclic compounds. In cyclic compounds, you have to start from the double bond. Okay, so you have to include the double bond in your nomenclature. So you don't start from down here. You have to start from where the 1 is. Okay, and so this is 1-methyl cyclohexene. If the double bond was not there, you would just call it methyl cyclohexene. Or hexane, but because the double bond is there, you have to give it a number now. Okay, so give the location of the methyl group, even though it might seem a little redundant. Little bit more on the nomenclature of alkenes, and this has to do with the cis and trans isomerism in alkenes. Alkenes have double bonds, and double bonds don't rotate, and therefore whatever orientation the groups are in, they will stay in that orientation. So let's take a simple molecule like butene. If the butene was on the first 2 carbons, we did not see this kind of a problem, but as soon as it's on 2 carbons in the middle, so it is 2-butene, then you can have 2 types of compounds. Okay, one is like this, in which the 2 hydrogens are on the same side, and another one where hydrogens are on the opposite side. When the hydrogens are on the same side, it's called cis, and when they're on the opposite side, they're called trans. And the reason we have to call them cis and trans is because this orientation stays the way it is. You cannot change that without breaking a bond, and therefore it is kind of like a constitutional isomer, but you can't call it constitutional because really the basic structure is the same. Hence, these are called the cis and trans isomers, or you can also call them geometric isomers. One of the things about the orientation of these molecules is that because it stays the way it is, its 3D structure also changes a little bit. So if you look at this one closely over here with the cis-2-butene, this kind of looks like a boat, all right? And that's what it would look like in the 3D orientation as well. And the trans-2-butene kind of goes like a zigzag as it would if it was a simple alkene. And so just a simple thing as a cis and trans isomerism gives a very different kind of a 3D shape to a molecule. So it's really important to know the cis and trans isomerism. One thing to keep in mind is the cis and trans isomerism is only for hydrogen atoms. You don't refer to it when you don't have hydrogen atoms. So for example, if I had CH3 groups and ethyl groups over here, I would not call it cis and trans. Okay, then there is a different nomenclature for that. So cis and trans is limited only to hydrogens. One other point to note is that cis and trans is not possible when two of the groups on one carbon are the same. So for example, if you look at this example here, the double bond carbon has two of the same groups on one carbon, and because of this it will not exhibit cis and trans isomerism. So even if you have two different groups on the other carbon, you can just flip the molecule and get the other one, and therefore these two actually are the same. So usually terminal alkenes where you have just the CH2 at the end will not show those kind of isomerism, which is why 1-butene does not show cis and trans isomerism, only 2-butene does. So if you have two similar groups on one of the carbons, you do not see cis and trans isomerism. The example below it shows that if you have to have two different groups in order to show cis and trans isomerism. In the next slide or so, we're going to learn about how to do the naming. Now, since the cis and trans isomerism is limited only to hydrogens, what do you do if you don't have just hydrogens? Okay, so for example, if you look at this molecule down here, which is 2-chloro-2-butene, here you don't have hydrogen. So how do you decide which group goes where? Because just like stereochemistry, these groups are stuck in a particular orientation. So you need to know where exactly to put these groups when you draw it out. So in that case, we use the same nomenclature system we did back in stereochemistry, the Kahn-Ingold pre-log system, where you assign priorities according to atomic weight. All right, so you look at what is lower and what is higher. And so the best thing to do is to take a double bond and slice it into two, okay, in the middle. And on both sides then, you label what is lower and what is higher. Okay, and so if the higher groups are on the opposite sides, they're called E. And if the higher groups are on the same side, they're called Z. Okay, so Z for same side. Okay, and so that is how we do, and this is called the E and Z nomenclature for alkenes. So in this case, there is no cis and trans. You cannot use cis and trans because there is no hydrogen. So in these cases where there is no hydrogen, you have to use the E and Z nomenclature. So in this case where we have 2-chloro-2-butene, here you slice it into two, and then you look at the higher priority group, which in this case is the methyl group. All right, and then on the other side, on the right hand side, the chlorine is the higher group. All right, and so this becomes an E kind of a nomenclature. If you were confused and if you were thinking that you could use methyl groups as cis and trans, you would get this wrong, because technically this is not cis. Okay, so the methyl groups have nothing to do with the priorities over here. Okay, so this is not cis, this is actually trans. Okay, in some ways, in the most crude way possible, but otherwise the official nomenclature is E. So just like R and S, you put the E in the brackets and then dash and 2-chloro-2-butene. Okay, and then if they're on the same side, the high priority groups, then you call it E. And regarding the priority rules, they are exactly the same as stereochemistry, and in case you've forgotten it, they are on the next slide. So here are your priorities, okay, for different groups, and go through them again because this is the same thing as stereochemistry. It's all based on atomic weight, and it's based on atom by atom by atom. Don't take the whole group, okay, atom by atom. So a few more examples for E and Z. Now with the 2-butene, okay, we did this with cis and trans, but you can also do it with E and Z. And so IUPAC will accept both, and the only way it will accept both is, of course, if there are hydrogens. But the best way to make sure that you have exactly what you're talking about is give E and Z nomenclature. So here, when you have both groups on the same side, it is Z, and when they're on the opposite sides, they are E. And so on the same side, this is, of course, the cis, and then we have the trans, okay, over here. So here are some more examples. Again, slice this into two, and then chlorine is the heavier atom, and then bromine here is the heavier atom, so this becomes E, and so on and so forth. Okay, so that's kind of how you decide on the priorities of groups and do the E and Z nomenclature. A little bit about stability of alkenes. We kind of went through this a little bit in the elimination chapter, because in elimination we learned about Zaitsev's rule, in which you form the more stable alkene. So just a little bit more, okay, about the substitution. So the more substituted the alkene is, the more stable it is going to be. Okay, and when we say substituted, it means it has alkyl groups around it. So here, if you look on the left-hand side, then we have all alkyl groups around the double bond, and on the right-hand side, we have no alkyl groups at all. So this is just ethene, and ethene is the least stable of all of these alkenes. So again, the more substituted an alkene is, the more stable it is going to be. All right, and then cis alkenes, or excuse me, trans alkenes are more stable than cis alkenes. Now, hopefully you will not have to decide between these two, and you know, hopefully you'll be spared for that one. But of course, with the 4 substituent versus 3 versus 2 and 1 and none, okay, you will have to do at least that much. Okay, so more substituted the alkene, the more stable it is. One other property of alkenes, which was not present so far in any of the compounds that we've talked about, is degree of unsaturation. Okay, so this is something I mentioned to you a long time ago, but not quite as a property of an alkene. This was when we were talking about constitutional isomers. And so I mentioned to you about how to use this formula, the CnH2n plus 2 and the CnH2n formula, to figure out if you had any double bonds or not, okay, in that molecular formula. So now we're going to use it a little bit more professionally and figure out some degrees of unsaturations. Let's look at a few other things before we actually get into the examples. Is if you have some other elements in your compound other than carbon and hydrogen, then how do you deal with the degree of unsaturation? So for example, if you have halogens in there, then how do you do it? You replace the halogen with the hydrogen, and then you calculate for the number of hydrogens you should have. So for example, if you have C4H6Br2, then the Br2 you will add on as 2 hydrogens, okay, and so therefore it will be C4H8, all right, and then you calculate for the hydrogen deficiency index from there, so which is CnH2n, therefore it has 1 degree of unsaturation, okay. So for halogens, just replace it with hydrogen. For oxygen compounds, oxygen don't really affect anything in the formula because the oxygens will just fit in. Okay, so they just fit in between the 2 bonds between carbon and hydrogen and whatever it is. And so oxygens don't really matter that much. So you can ignore the oxygen in there, okay, which is really nice, convenient thing to do. And then with nitrogen compounds, you have to subtract the nitrogen and 1 hydrogen, okay, and that is because nitrogen have 3 connections in there. So for example, if you have C5H9N, then you remove the nitrogen, but you also remove a hydrogen, okay, so C5H9N becomes C5H8, okay, so remove the nitrogen and remove a hydrogen, okay, if you have nitrogen containing compounds. Let's look at some examples, okay, of solving for degree of unsaturation or hydrogen deficiency index. So the first problem, isopentyl acetate has a molecular formula of C7H14O2. So calculate the HDI. According to what we just learned, we can ignore the two oxygens, okay, because they will just fit in. So which means that our formula is C7H14. Then you take the alkane formula CnH2n plus 2 and then calculate the number of hydrogens an alkane would have if it had 7 carbons, which is 16. So then putting it in our formula, 16 minus 14 divided by 2, it gives us the HDI of 1, okay, or degree of unsaturation is 1. And that means that we have either one ring or one double bond, okay, and it turns out that the structure for isopentyl acetate does have a double bond, okay, in it. So if you're given as a multiple choice question, you should be looking for the double bonded oxygen, okay, in there, or something that has a ring, okay, in it. So, but this is isopentyl acetate and that's the structure. The next one, calculate the HDI for niacin. And the molecular formula is C6H6N2O. Again, we're going to ignore the oxygen, all right, because oxygen just fits in, as we just said. For nitrogen, we have to remove the two nitrogens, and remember, one hydrogen goes with each nitrogen. So if we are removing two nitrogens, we also have to remove two hydrogens, okay, with it. So when we do that, our new formula is then C6H4. So if we have 6 carbons, then we calculate how many hydrogens we should have for 6 carbons, which is actually 14. And so then 14 minus 4, 4 is what we have in our formula, and that is 10 divided by 2 then would give us the hydrogen deficiency of 5, which means we have 5 degrees of unsaturation. So here is our formula, and here we have a ring. We have 3 double bonds and 1 double bond outside. So 4 double bonds and 1 ring. That gives us a hydrogen deficiency index of 5. Let's do another example. And here we have a formula of C6H10. And the question is saying that propose as many structures as possible, okay, for C6H10. So the first thing that we do is find out the number of hydrogens that are missing. And for alkane, if we had 6 carbons, we would have 14 hydrogens. So therefore, 4 hydrogens are missing. So 4 divided by 2, which means we have 2 degrees of unsaturation, which means that we could have 2 double bonds, 1 triple bond, 2 rings, 1 ring, and a double bond. Okay, and so with all of these possibilities, here are the structures that are possible for C6H10. Okay, so here we have 2 double bonds, here we have a triple bond, here we have a bicyclic structure, and then here we have a ring and a double bond. You can draw another constitutional isomer for cyclohexene. You could have cyclopentene with a methyl group. That's a whole different thing. You can have any kind of diene, provided that you have all the carbons there. Okay, that's the most important thing. So here are some structures that are possible if you had C6H10. So in a way, this is like constitutional isomers, but you have a little bit more information now. Now for the physical properties of alkenes. Alkenes are very similar to alkanes, okay, for most of their properties. So the boiling points will also resemble alkanes, which means they generally have low boiling points. And the intermolecular force is primarily going to be the van der Waals force, or the London forces, and dispersion forces. Dispersion forces come into play when you get to the higher molecular weight. And as the molecular weight increases, the boiling point will also increase because of the dispersion forces. So that's kind of how it goes for the boiling points. Regarding the solubility in water, they're going to be insoluble in water because, again, water is polar and alkenes are non-polar. The intermolecular forces again, okay, because they have van der Waals forces, which is not a very polar force, okay, intermolecular force. So they're insoluble in water. Density is less than water, as it is with alkanes, which means that they will float on water. That's the reason why we find out about the density and compare it to water. And the odor. Alkenes have a very specific odor, okay, they're very unique in their own way. Some can be classified as good, some are bad, some are just, don't know, organic, okay, in nature. So in any case, they all have some or the other forms of odor, okay. So let's look at application of alkene. And here the first type of alkenes that to talk about are actually the ones that smell, okay, and fragrances and flavors, okay. These are called terpenes, and terpenes have this kind of a structure where there are dienes, and they have 5 carbon skeleton, 1, 2, 3, 4, and then the fifth one is coming out from there. And this is called isoprene, and isoprene belongs to this class of compounds called terpenes. In any case, it doesn't have to have 2 double bonds, but in some ways the skeleton is kind of like isoprene. These compounds, terpenes, are very fragrant compounds. They have all sorts of nice odors, and they're usually used in perfume industry. And here is the structure for camphor, which we know smells wonderful. Pinene is the smell of pine sol. And so they have wonderful fragrances, okay? And so this is one class of compounds. Other class of compounds where you find alkenes is in fatty acids. And fatty acids will have all sorts of double bonds. Now these two, if you can take a look at this, you will see that this is actually a cis bond, and here also it is a cis bond, okay? When we talk about fatty acids later on also, we will talk a little bit about the cis and trans nature of fatty acids. And then vitamin A and E, they're also long-chain fatty acids in a way. And again, look at that. We have cis bonds over here. So these are some places where you find alkenes. We will talk a lot more about alkenes after we've done the reactions of alkenes, because right now you know only about the nomenclature and some physical properties, but not chemical properties. So once you know that, then we will talk more about this. One interesting thing about alkenes is that they're really important in the chemistry of vision. And if you want to read more about it, you go ahead to this link and read about it, because it's just a matter of geometric isomerism for us to actually see anything. So it's a really interesting thing that such a simple thing can make vision possible in our eyes. So for this chapter, we really don't have a whole lot, just a little bit of things. You have to know the nomenclature. You should know the cis and trans, geometric isomerism, the E and Z nomenclature, stability of alkenes, how to calculate the hydrogen deficiency index or the degree of unsaturation, and some of the properties of alkenes, not the application, okay, but just the properties, which means you should be able to predict their boiling points and solubilities. Okay, so that is just this part. In the next section, we're going to talk about the synthesis of alkenes, and then we'll go on to reactions.